Hello and welcome. My name is Alan. We are back with more ideas and opinions of Albert Einstein. We are continuing to read Physics and Reality. We are now reading section 4, The Theory of Relativity. There is no inductive method which could lead to the fundamental concepts of physics. Failure to understand this fact constituted the basic uh, philosophical error in so many investigators of the 19th century. It is probably the reason why the molecular theory and Maxwell's theory were able to establish themselves only at a relatively late date. Logical thinking is necessarily deductive. It is based upon hypothetical concepts and axioms. How can we expect to choose the latter so that we might hope for the confirmation of the consequences derived from them? The most satisfactory situation is evidently to be found in cases where the new fundamental hypotheses are suggested by the world of experience itself. The hypothesis of the non-existence of perpetual motion as a basis of the thermodynamic of for thermodynamics affords such an example of fundamental hypothesis su- suggested by experience. The same holds for Galileo's principle of inertia. In the same category, moreover, we find that the fundamental hypotheses of the theory of relativity, which theory has led us to an unexpected expansion and broadening of the field theory, and to the superseding of the foundations of classical mechanics. The success of the Maxwell-Lorentz theory has given great confidence in the validity of the extra or electromagnetic equations for empty space, and hence, in particular, in the exertion that light travels in space with a certain constant speed c. Is this assertion of the constancy of the light velocity valid for the inertial system? If it were not, the one specific inertial system or reference would be distinguished, or more accurately, one specific state of motion of a body of reference would be distinguished from all the others. This, however, appeared to contradict the mechanical and electromagnetic optical experimental facts. For those reasons, it is necessary to raise the rank of a principle of validity of the law of constancy of light velocity for all inertial systems. From this, it follows that the spatial coordinates x2, x1, x2, x3, and the time x4 must be transformed according to the Lorentz transformation, which is characterized by the invariance of the expression d times x squared equals dx1 squared plus dx2 squared, and dx3 squared minus dx4 squared if the unit of time is chosen from the matter that the speed of light c equals 1. By this procedure, time lost its absolute character and was adjoined by the spatial coordinates of the algebraically nearly similar character, and the absolute character of time and particularly of simultaneity was destroyed, and the four-dimensional description was introduced as the only adequate one. In order to account also for the equivalence of all inertial systems with regard to the phenomena of nature, it is necessary to postulate um, invariance of all systems of physical equations which express general laws and expect the Lorentz transformations with respect to the Lorentz transformations. The elaboration of this requirement forms the content of the special theory of relativity. This theory is compatible with the equations of Maxwell, but it is incompatible with the basis of classical mechanics. It is true that the equations of motion and material point can be modified, and with them the expressions for momentum and kinetic energy of the material point in such a manner as to satisfy the theory. But the concept of the force of interaction, and with it the concept of potential energy of a system, lose their basis because the concepts rest upon the idea of absolute simultaneity. The field, as determined by differential equations, takes the place of force. Since the foregoing theory allows the interactions only by fields, it requires a field theory of gravitation. Indeed, it is not difficult to formulate such a theory in which, as in Newton's theory, the gravitational fields can be reduced to a scalar, which is the solution of a partial differential equation. However, the experimental facts expressed in Newton's theory of gravitation lead in another direction, that of the general theory of relativity. It is an unsatisfactory feature of the classical mechanics that in its fundamental laws and the same mass constant appears in two different roles, namely as inertial mass in the law of motion and as gravitational mass in the law of gravitation. As a result, uh, the acceleration of a body in a pure gravitational field is independent of the material of its material, or in a uniformly accelerated coordinate system accelerated in relation to an inertial system, the motions take place as they would in the homogeneous gravitational field in relation to the motionless system of coordinates. If one assumes that the equivalence of these two cases is complete, then one attains the adaptation of our theoretical thinking to the fact that the gravitational and inertial masses are equal. From this follows that there is no longer any reason for favoring, as a matter of principle, the inertial systems. And we must admit, on an equal footing, also nonlinear transformations of the coordinates x1, x2, x3, x4. If we make such a transformation of a system coordinates of the special theory of relativity, then the metric dx squared, or ds squared, equals dx1 squared plus dx2 squared plus dx3 squared minus dx4 squared goes over into the Riemannian metric of the form dx or ds squared equals g mu v dx mu dx3 summed over mu and v, where the g mu v symmetrical in mu v are certain functions of x1 through x4, which describe both the metric properties and of the gravitational field in relation to the new system of coordinates. The foregoing improvement in the interpretation of the mechanical basis must, however, be paid for in that, as becomes evident on closer scrutiny, the new coordinates can no longer be interpreted as results of measurements on rigid bodies and clocks, as they could in the original system, an inertial system with vanishing gravitational field. The passage of the general theory of relativity is idealized by the assumption that such a representation of the field properties and of space already mentioned by functions g mu v, that is to say by the Riemann metric, is also justified by the general case in which there is no system coordinates in relation to which the metric takes the simple quasi-Euclidean forms of the special theory of relativity. Now, the coordinates by themselves no longer express metric relations, but only the closeness of the objects whose coordinates differ but little from one another. All transformations of the coordinates have to be admitted so long as these transformations are free from singularities. Only such equations as are covariant in relation to the arbitrary transformations in this sense have meaning as expressions of general laws of nature, postulate, or general covariance. The first term in the general theory of relativity, the first aim in the general theory of relativity was a preliminary version which, while not meeting the requirements for constituting a closed system, could be connected in a as simple a manner as possible with directly observable facts. If the theory were restricted to pure gravitational mechanics, Newton's gravitational theory could serve as a model. This preliminary version may be characterized as follows. 1. The concept of the material point and of the mass is retained. A law of motion is given for it, this law of motion being the translation of the law of inertia into the language of the general theory of relativity. This law is a system of total differential equations. The system characteristic of the geodesic line. 2. Newton's law of the interaction of gravitation is replaced by the system of simplest generally covariant differential equations, which can be set up for the G-movie tensor. It is it is formed by equating to zero the once contracted Riemannian curvature tensor R mu v equals 0. The formulation permits the treatment of the problem of the planets. More accurately speaking, it allows the treatment of the problem of motion of material points of practically negligible mass in the centrally symmetric gravitational field produced by the material point supposed to be at rest. It does not take into account the reaction of the moving material points on the gravitational field, nor does it consider how the central mass produces this gravitational field. Analogy of the classical mechanics shows that the following is a way to complete the theory. One sets up as field equations R U R alpha or A. I'm not sure. I can't hardly read that. RU minus 1V or 1 half G U R equals negative T U, where R represents the scalar of the Riemannian curvature. Tu the energy tensor of the matter of the phenomenological representation. The left side of the equation is chosen in such a manner that the divergence appears identically. The resulting disappearance of the divergence of the right side produces the equations of motion of matter in the form of the partial differential equations of the case where Tu introduces for the description of the matter only four further independent functions. For instance, density, pressure, and velocity components, where there is between the latter an identity and between the pressure and density an equation of condition. By this formulation, one reduces the whole mechanics of gravitation to a solution of a single system of covariant partial differential equations. The theory avoids all of the shortcomings which we have charged against the basis of classical mechanics. It is sufficient, as far as we know, for the representation of the observed facts of celestial mechanics. But it is similar to a building, one wing of which is made of fine marble, left part of the equation, and the other wing of which is built of low-grade wood, the right wing of the equation. The phenomenological representation of matter is, in fact, only a crude substitute for the representation which would do justice to all known properties of matter. There is no difficulty in connecting Maxwell's theory of the electromagnetic field with the theory of the gravitational field, as so long as one restricts himself from the space free of ponderable matter and free of a electric density. All that is necessary is to put on the right hand side of the above equation for Tu the energy tensor of the electromagnetic field is empty space, and to adjoin to the so modified system of equation, the Maxwell field equation for empty space. Written in general covariant form, under these conditions, there will exist between all these equations a sufficient number of differential identities to guarantee their consistency. We may add that this necessary formal property is the total system of equations, or total system of the total system of equations, leaves arbitrary the choice of the sign of the member Tu, a fact which later turned out to be important. The desire to have for the foundations of the theory the greatest possible unity has resulted in several attempts to include the gravitational field and the electromagnetic field in one unified formal picture. Here we must mention particularly the five-dimensional theory of Kaluza and Klein. Having considered the possibility very carefully, I feel that it is more desirable to accept the lack of internal uniformity of the original theory, because I do not think that the totality of the hypotheses at the basis of five-dimensional theory contains less arbitrary features than does the original theory. The same statement may be made for the projective version of the theory, which has been elaborated with great care, and particularly by uh, Danzig and by Pauli. The foregoing considerations concern exclusively the theory of the field free of matter. How are we to proceed from this point in order to obtain a complete theory of atomically constituted matter? In such a theory, singularities must certainly be excluded, since without such exclusion, the differential equations do not completely determine the total field. Here, in the field theory of general relativity, we meet the same problem of the field theoretical representation of matter as we met originally in connection with the pure Maxwell theory. Here again, the attempt of a field theoretical construction of particles leads apparently to singularities. Here also the endeavor has been made to overcome this defect by the introduction of new field variables and by elaborating and extending the system of field equations. Recently, however, I discovered, in collaboration with Dr. Rosen, that the above mentioned simplest combination of the field equations of gravitation and electricity produces centrally symmetrical solutions which can be represented as free of singularity. The well-known centrally uh, systemmetrical solutions of Schwarzschild for the pure gravitational field and those of Reisner for the electric field with consideration of the gravitational action. We shall refer to this shortly in the paragraph next, but one. In this way, it seems possible to get the matter and its interactions a pure field theory free of additional hypotheses once or one moreover whose test by submission to facts of experience does not lead to the difficulties rather than purely mathematical ones, which difficulties, however, are very serious. So, yeah. Einstein really getting into the minutia of the theory of relativity in relation to the field theories. Yeah, we're really getting to stuff I am not uber familiar with myself because I have never taken physics. Um, I know some of the base ideas, but yeah, we're really getting into the minutia of some of Einstein's material. But I want to thank you all for watching. As always, educate thyself. Think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.